Having discussed greatest common factors, we're now going to move on into a little bit of discussion of least common multiples. But before we can talk about it, we have to define it. Suppose a, b, and c are all integers. A is a factor of c, in other words, c is a multiple of a, and c is also a multiple of b. Then c is a common multiple of both a and b. And if, furthermore, c is the smallest positive integer, which is a common multiple of a and b, we say it's the least common multiple, or LCM, of the two integers a and b. We can also use the notation of these square brackets. Remember that parentheses around a and b meant the greatest common divisor. Square brackets around them is going to mean the least common multiple. Well, here's a theorem. If either one of the two numbers is 0, then the least common multiple of a and b doesn't even exist. If, however, they're both not 0, then it does exist, and the least common multiple of a and b is less than or equal to the absolute value of the product. Well, the only multiple of 0 is 0 itself. So if either number is 0, the only number that could possibly be a common multiple is 0 again. But we did require, back up at the original definition, that to be called the least common multiple, you have to be the smallest positive integer. This is kind of cooked into the definition that only positive integers can be called the least common multiple. So if one of the numbers is 0, the only possible common multiple is 0, which isn't positive. So there would be no positive common multiple, there would be no LCM. Okay, so if either one of the two numbers is 0, there is no least common multiple at all. But let's suppose they're both non-zero. Well, the absolute value of a times b is divisible by a. A can be factored out of it right there, but it's also divisible by b. So this number is a common multiple of both a and b. Since a and b were non-zero, this absolute value is positive. So since positive common multiples do exist, there is a smallest one to find. And the smallest common multiple would not be larger than one common multiple we've already found. If you find a single common multiple, maybe there's a smaller one, in which case that might be the LCM, or maybe not, in which case you already found it, but in any case, the least common multiple can't be bigger than one you've already found. Which is to say, the least common multiple cannot be bigger than one particular number that is a common multiple. Let's look at an example. Find the least common multiple of 36 and 24. Well, both are non-zero, so there is an LCM to find. In this example, we're just going to use brute force, listing out multiples of each number and finding the smallest number that belongs to both lists. So here are the first 5 or so multiples of 36, and here are the first 5 or so multiples of 24. Well, the smallest number that shows up in both lists is 72, so that must be the smallest common multiple. There we have it. The LCM of 36 and 24 is 72. We were lucky in this example that the least common multiple showed up pretty quickly. We do, however, know that the least common multiple is no larger than the absolute value of the product. So in theory, if we went all the way out in both lists to 36 times 24, so I keep listing out multiples of 36 until I reach 864, and I keep listing out multiples of 24 until I reach 864, then I will have a common multiple, specifically 864, and maybe I will have found one earlier. But by that point, the LCM will definitely have shown up. However, we did find a very quick way to compute greatest common divisors, the Euclidean algorithm. Perhaps there is also an easy way to compute least common multiples. Well, here's going to be a preliminary result along those lines. Suppose a and b are positive integers, and c is another positive integer that is a common multiple of both of them. Then c is a multiple of the LCM. In other words, any common multiple we find c must be a multiple of the LCM. This is analogous to a result we had about common factors. Any common factor of two numbers must be a factor of the GCD. This is saying any common multiple of two numbers must be a multiple of the LCM. So C is one particular common multiple, and the LCM is the smallest positive common multiple. So the smallest possible positive common multiple can't be any bigger than one common multiple that we happened to find. If we apply the division algorithm between these two numbers, we can write C is equal to the LCM times Q plus some remainder, and this remainder could be 0, but it can't be as large as whatever this number here is. Okay, we're just applying the division algorithm to say C is equal to this times something plus a remainder, and remember that remainder is strictly smaller than what we attempted to divide out. So we're going to rearrange this as R is equal to C minus the LCM times some integer Q. Now A is a factor of C, that was one of our givens. A is definitely a factor of the LCM of A and B because this is a common multiple of A and B. So if A is a factor of two numbers, then A is a factor of any linear combination, specifically C minus Q times the LCM. In other words, A is a factor of R. You can do the same work using B instead of A. B is a factor of C. B is definitely a factor of the least common multiple, therefore it's a factor of any linear combination, specifically R. So B is also a factor of R. R is therefore a common multiple of A and B. R is a multiple of A, R is a multiple of B. But the LCM is the smallest positive common multiple. Notice up here, R is smaller than the LCM. Okay, R is also a common multiple. The LCM is the smallest positive common multiple, so R being less than this is fine, but we can't have R being positive. If R is a positive number, I have a smaller positive common multiple than the smallest positive common multiple. So we have this string of inequalities here, but now we know that R can't be positive, otherwise this wouldn't have been the smallest positive common multiple. Well, if R can't be positive, it must be 0. And if I look up here, if R is 0, then C must be exactly a multiple of the LCM. And that's what we were trying to show. So any common multiple of A and B will be a multiple of the LCM. We're now going to relate the notion of least common multiples and greatest common divisors to one another. Specifically, we're working towards an effective way of computing least common multiples. It's the following theorem. If A and B are both positive integers, then the least common multiple times the greatest common divisor is just the product A times B. Notice if either one of the two numbers is 0, then the LCM doesn't exist. So in order for this formula to make any sense, for the LCM to exist, they both have to be non-zero, and we're just going to use positive integers. Well, A times B is A times something, so it's a multiple of A. But it's also B times something, so it's a multiple of B. So A times B is a common multiple of both A and B. But we know from the previous slide, any common multiple of A and B is a multiple of the LCM. So the LCM is a factor of AB. Well, if the LCM is a factor of AB, then I can find an integer x so that the LCM times x is the number AB. But next, the LCM is a common multiple of A and B by definition. So it's a multiple of A, so I can find a solution to AM equals the LCM. But it's also a multiple of B, so I can find another integer so that Bn is the LCM. Now we're going to claim that whatever m and n we solved for here have to be relatively prime to one another. We happen to know from our work with Bézout's identity that m and n can both be written as their GCD times something, where those two things are definitely relatively prime to one another. We can always take two numbers and write them as their GCD times what's left, and what's left will be relatively prime. This came from our work with Bézout's identity. Therefore, we can string a bunch of stuff together and get the following. Here we have A times the GCD of m and n times I. But this product here was exactly m up here. So this is A times m. But A times m is exactly the LCM right there. But the LCM was also Bn, here we are, and n was equal to this GCD times j. So overall, A times the GCD times I equals B times the GCD of m and n times j. So we take this equality and cancel out the factor of the GCD of m and n to get A times I equals B times j. Now the left is definitely a multiple of A, it's A times I. The right is definitely a multiple of B, it's B times j. So whatever this single number is, they're equal to each other. It's a multiple of A and it's also a multiple of B. So whatever that number is, it's a common multiple of A and B. If it's a common multiple of A and B, and everything on the board here is positive, it's at least as large as the smallest common multiple of A and B. But the smallest common multiple of A and B we wrote as A times M. So A times I is bigger than or equal to A times M. In other words, I is bigger than or equal to M. But the GCD of M and N times I equals M. I is bigger than or equal to M. So this number is bigger than or equal to that one, and all of these are positive. The only way that works out is if the GCD of M and N is 1. So up here we wrote the LCM of A and B is AM, but also BN. And we've now shown that whatever those M and N are, they're relatively prime to one another. Okay, so let's continue our discussion here. The GCD of A and B is a factor of both A and B, which means there's some solution to alpha times the GCD equals A and beta times the GCD equals B. But since it's the smallest common factor, these two things that are left over must be relatively prime. A and B are written as the GCD of those two numbers times whatever is left over from the respective factoring, and those two leftover bits are definitely relatively prime to one another. Combine it with the earlier equality where AM equals BN equals the least common multiple. And here we have A is alpha times the GCD, A times M, is the least common multiple is BN, but B was beta times this GCD. Cancel the GCD out and we get alpha M equals beta N. So we can conclude a lot now. Alpha times M is beta times N. So these two numbers are the same number. Alpha is definitely a factor of this number, which means it has to be a factor of this one because they're the same number. So alpha is a factor of beta N. But since alpha and beta are relatively prime, if alpha is a factor of beta times N, alpha must be a factor of N. So if alpha is a factor of N, let's write it that way. N is alpha times something. But similarly, if beta is a factor of beta M, which is the same as alpha M, then beta is a factor of alpha M, but since alpha and beta are relatively prime, beta must be a factor of M. So let's write M is beta times some other integer. We can combine a bunch of pieces that are floating around to get the following. Alpha beta y2 equals beta alpha y1. Where did this come from? Beta y2 is M. This is alpha M. But alpha M is beta N, and N was alpha y1. So from alpha M equals beta N, now we can cancel out the alpha beta and just get y1, y2. Whatever this common value is, we're just going to call it y. So wherever I had a y1 or a y2, since they're the same number, we're just going to call it y. So specifically, N is alpha y and M is beta y. But now we see that this number is a common factor of M and N. If M is beta y and N is alpha y, then y is a factor of both. But we've already shown M and N are relatively prime. So if I have a positive common factor of two numbers that are relatively prime, that number must have been 1. Now that we know y is 1, okay, stuff is starting to fall into place. If y is 1, then N is alpha and M is beta. If N is alpha and M is beta, we're going to start coming back earlier and earlier and get some interesting stuff. So A times B is alpha times the GCD times B, because this was A. All we do is move this around a little bit, move the alpha to the other side, okay? But now we have that N is equal to alpha, so I'm going to replace this alpha with N. But B times N was exactly the least common multiple of A and B. And we have finally shown that A times B is the greatest common divisor times the least common multiple. Here's an example of how that's useful to us. Compute the least common multiple of 125 and 45. Well, the product is easy enough. We just hack that out. The Euclidean algorithm allows us to quickly compute that the greatest common factor of the two numbers is 5. And therefore, 5 times the LCM is the product 5625. Divide both sides by 5 and we're done. The least common multiple of 125 and 45 is 1125. So this formula allows us to replace computing LCMs with computing GCDs, and since we already know a quick way to compute GCDs, now we have a quick way to compute LCMs. Okay. There are some elementary school type techniques for computing greatest common factors and least common multiples that are based around the prime factorization of A and B. But I do encourage you to forget these techniques. Prime factorization takes a lot of work. The Euclidean algorithm is much, much faster and much, much easier. Okay, we will revisit these techniques, which you might already know, but I just want to make clear, the Euclidean algorithm is so much faster and easier than trying to find prime factorization of numbers. And now we've seen that both LCMs and GCDs can be computed with the Euclidean algorithm. So this is just a better and easier way to compute these things compared to prime factorization techniques, which you might already know. So if you're asked to compute GCDs or LCMs, if you have prime factorizations already given to you, okay. Otherwise, use the Euclidean algorithm.